Hello, hello.
Afternoon.
Oh, good afternoon, good afternoon, good afternoon, Valentina. Okay, we're right. Hold on, I'm going to put something in. Wait, okay. Good afternoon, Valentina. Good afternoon, Dante. And I know I saw you guys in the waiting room for a while. I totally appreciate it. Very, very on time. More people. Uh, and someone just said that with their voice. Was that Valentina? I should have caught that. So, good afternoon, person who said that with your voice, which I really appreciate. Um, and good afternoon, Mario, and good afternoon, Bree, and good afternoon, Tuskeen, and good afternoon, Key, and good afternoon, Juliana, and good afternoon, Bradley, good afternoon, James. Hello, Samantha. Who did I miss? Obviously, well, I shouldn't say obviously. Hello, Charday. Good afternoon. Wait. Oh, good afternoon, Samantha M. Oh, I've been making that. Sorry. Good afternoon. Yes. And hello again, Charday. Awesome. Okay. Wait, who else? Okay. I think that's everyone. That's everyone. Okay. Okay. I'm gonna put something in the chat. More people are coming. I'm gonna put this in the chat again because I know. Okay. We're just getting rolling here. We're gonna get straight to the material again. I know we're in a time crunch. I know it stinks that you don't have your exams back. Good afternoon, Alexis. Good afternoon. Good afternoon, Michaela. Okay. I'm not gonna dwell on it. Hello, Dennis. There's no excuse or justification for me not having your exams yet. I will be releasing them one-on-one, like any minute. You're gonna start getting them, and you won't all get them at the same time because I'm just gonna release them as they go. I'm taking way too long on them. I apologize. I won't spend all, but I do know it's not good. Good afternoon, direct chat person. One of the reasons I just keep putting it in the chat, though, for I know as tense as it makes people not to have them back, it also I just want to own the fact. I will quickly say, I'm I don't say this to scare anybody. This is not the reason they're taking so long, but I am taking a little longer with them than usual. I'll just say this very quickly. You know, my whole approach to these exams is that all things that would normally be considered cheating are not cheating, right? On this, like you were allowed to use any kind of resource, you were allowed to, and that's correct. You were allowed to talk to anybody, help each other, go on the web, and that's all so that no one person has an unfair advantage over another person, especially so that one person doesn't get an advantage by breaking a rule that someone else went to great efforts not to break, if you see what I'm saying, right? The whole reason I have an approach, I have the approach, the whole reason I do the exams the way I do is so that it's a level playing field for everybody, right? And so then the only thing that but then when what I'm looking for, as you know, when I'm grading them, is I'm looking to see that you actually understand what it is that you're writing down when you write it down, which I can tell, but I can only tell if I'm very careful and I take time and I treat each exam seriously. So I do want to make it clear that there's some reasons for me to take that very seriously this semester. I'll leave it at that for the moment, but you will get them back soon. You will get them in time for what you need for the final exam. We will talk about the final exam tomorrow, Monday. You will be prepared. The final exam will be shorter than this one was. I can tell you that right now. That always happens anyway, but especially in a 5-week course. And the final exam will not be cumulative explicitly. Explicitly, it'll only cover the material that we've done since the midterm for whatever that's worth. But we're not going to get into all that right now. Just another way of saying, I know you need them back and you will get them back, and they are not forgotten or anything like that. Yeah, maybe the other reason I keep saying it, I mean, I guess to dovetail, is that one thing that I feel like I've gotten from many of you in an unusual way, is I feel like many of you, even when you have an issue with this or that, or a concern or a question or a confusion, or you feel like you didn't do something as well as you could have or something like that, I feel like many of you have been very good about communicating that to me, or communicating in advance if you had a special circumstance or a special need. I feel like communication in general is like the hallmark of integrity and honesty. And so maybe I'm over communicating this one thing that I feel guilty about. but I do want to reach out again and say that the more we can all communicate with each other and be super clear on where we think we're good or where we think we're not so strong, I think the more integrity pervades throughout the entire group. And I think integrity is in general pervading through this group. But when questions arise or when concerns arise, they often can be straightened out by good communication, and often perhaps they come about maybe sometimes for, I'll just say they can be straightened out by good communication. So good communication is something I'm in favor of. Okay, let's do some physics. If you have no idea what I'm talking about, then good, by the way. But if you feel like you know what I'm talking about, then maybe that means you've either already talked or it would be beneficial for us to talk a little bit more. Okay, here, and there's more people saved by the bell. All right, what we're going to get to today to keep the material rolling, we're going to get to that homework sheet that I think we said in theory is due tomorrow. So in theory, like nothing new is due today. I still owe some of you points or more points from old assignments. You still can upload revisions on old assignments. Like no portal has been changed or anything like, or has been taken down or anything like that. But the assignment that's on the docket now, that's in theory due tomorrow, we're going to get to explicitly today. So anything I say about it today that helps you do that assignment, great, no problem, as long as you understand it. Anything I don't get to today, then you'll work through on your own. So I guess I'll go straight to it. Yeah. Okay, I'll go straight to it. Yeah, so I'm going to switch screens for a minute, just so you see where I'm at. For a minute, I'm going to switch what I'm going over. What I'm going over is this. We're going to start. No, it's not. See, I'm working on that. No, it's this. Okay, I'm going to start talking about this sheet right here. Hopefully you can see. Wait, are there 11 people in the, wait, are there a lot of people in the waiting room? No. Sorry, two devices getting me crazy. Okay. This sheet that this sheet that you see on your screen right now is the sheet I'm talking about. This is what is, I believe, technically due tomorrow, the beginning of class. For what it's worth, also, I think it's the last official assignment that we officially do as an assignment. From all next week, whatever we do is just all in service of trying to catch up with each other and get you prepared for your final exam. Like, I think this is the last official homework for what it's worth. If that helps reassure you in any way. So this is the sheet I'm talking about. In a minute, I'm going to start going through it. So I'm going to switch screens again. So I guess I'm asking you to take this out on your own side. But you see the first beginning of this sheet, right, hopefully strikes you as a review with a mistake. There should be a negative sign in that first equation. Holy smokes. There should definitely, I don't think I can adjust it right here on screen, but there should be a negative sign in that gravity equation, but that's what we spent all of yesterday talking about. Then we made a comparison and said, okay, the Coulomb interaction between two, why is there such, okay, the Coulomb or electrostatic interaction between any 2 point charges, Q1 and Q2, is given by an equation that absolutely resembles the universal gravitation equation. Same mathematical form, same inverse R squared form, same vector character, right? The difference is in the magnitudes, like the numbers will come out differently for the electrostatic force due to charges from what they will come out for the gravitational force due to masses. But then also there's a directional difference in that electrostatics can be a pull or a push. It can be negative, as in I exert a force on you that is directed toward me, right? That's what we mean by negative. That's what we mean by pull. That's what we mean by attractive. That's what one mass does to another. That's what a proton does to an electron, or what an electron does to a proton, or the electrostatic force between 2 point charges can be positive, can be I exert a force on you that is in the same direction as the displacement from me to you, right? That would be a force that has the same direction as the displacement vector. That would be a positive sign. That would be repulsion, right? That's the summary of what we were saying yesterday. Then it says here on the sheet, so this whole sheet is just summarizing what we said yesterday, right? It's giving you the Coulomb constant of proportionality, measured in Newton's meter squared divided by Coulomb squared, just like we said yesterday. Oh, there's something in the chat. I'm sorry. Hang on. Oh. Okay. Wait, that's a great, okay, that is a very honest question. That's a good example of good communication. Okay. So Alana, because it's public, like, thank you, Alana. Definitely submit for points for this. Alana in the chat to everyone is saying, can you just remind me of what I mean with R with the caret on top of it? Okay. That's oh, sorry. I'm sorry.
I don't know if it can help Alana, but yesterday he said the R with the hat, or he calls it a caret, is the unit vector, and it is defined by R, the vector, divided by is it the double absolute value of?
Right, the magnitude. Good. Yes. Keep it. Yes, it is. Keep going. Good. You don't have to put, as long as you keep going. Yes, it is. Keep going. That's good.
And when we talk about the R with the hat, we just need to remember that it's always going to equal to 1. Let's say you had a magnitude of 3, you're going to end up getting 3 divided by 3, which is going to give you 1, and it basically focuses on the direction. So it's basically direction, if you want to put it that way.
Yes. Okay, that is awesome. Now, for anybody who's listening right now, I'm going to repeat. I'm going to write down in my handwriting what Christopher just said. But I want to say this, the whole dialogue that just happened. If you think I'm a point fairy for wanting everybody to get points for that, then good. Think I'm a point fairy. Like, if you think I'm overly but like, nothing could be better to me than the fact that one person just asked what she asked, and then another student gave like his best answer to the question. Like, that tells me a lot about this class. I'm still going to answer it my way right now for everybody, because this is an important and new thing. And I'm going to say, before I write it down, what Christopher just said is correct. I'm not going to correct what he said at all. If it worked for anybody in the room, if it worked for Alana, even better. And if anybody even wants to put in the chat, like, yeah, that worked, or that clarified it, or whatever, fantastic. Like, there's actually literally no, I mean, the only thing I'm going to add to what Christopher just said is that I'm going to write it again in my handwriting so you can write it in your notes. So I'll do that right now. But yeah, the question is great. The answer is great. And neither of them is a waste of anybody's time. And even for those of you who think you already got it, if you're sitting there right now going like, yeah, that's what I thought. Okay, that's what I thought. I'm good. Okay, then good. Then you can feel even stronger now, because we're all triply confirming it. Because this is one of those things that is so simple. It seems easy, but it isn't easy. And it comes up so much that if you don't catch it at the beginning, you're lost for a long time. I was lost for a long time if I didn't catch it at the beginning. So, okay, so I'm just going to write it again. But it's also, let me just make it really clear too, what Alana's asking when she says, can you just remind me? So, okay, so Christopher just reminded her. I'm going to remind her again. I mean, to be fair, we spent like 2 hours on this yesterday. Like, so I can't, like, so I'm just going to summarize, right? I mean, this was like practically, so it's not a minor question like, oh, I just forgot. It's like the whole lesson of yesterday. But but it's worth that she's asking. Okay, I'm over talking this, but it takes guts to basically ask something that just got covered. But I'm so glad she did, because I know in my heart that this escapes people all the time. And particularly if they think it's just a detail. Anyway, so here it is. What Christopher just answered to, but I will ask, but that that when we're done with this, that Alana, even privately, put in the chat whether she thinks it's clear now or not. And I will ask anybody else besides Alana or Chris, put something in the chat to say it's clearer now, or it was always clear, or it's too clear. Move on already, Avram, something. But this is definitely a big deal. This is what it means. What Christopher just said is this. Okay. Also, I'm going to try to cheat a little bit. Oh, wait, someone's in the waiting room. Sorry. So, okay, hold on. I'll explain this. Okay, in sum again, and again, this is in agreement with, it's just like my perspective on what Christopher just said, but he got it right. Remember, if you have some vector R, any vector, right? So it's a vector, so it has magnitude and direction. We decided yesterday that if you just write the symbol itself, R, without the arrow above, then you're just talking about the pure size, the pure magnitude of that vector. Right. So what we're saying is, if you take a vector, if you take an arrow with a certain direction and a certain size, and you divide that arrow by its own size, which sounds like a really weird circular thing to do. But and again, just to extend off Christopher's example, if you have an arrow that's 3 meters long, pointing due north, right? And then you divide, so that would be an example of R, vector, because we're talking about a displacement vector here. So you got a vector, an arrow that's 3 meters long pointing due north. What we're saying is take that arrow that's 3 meters long that's pointing due north and divide it by 3. Divide it by its length, which is 3, right? Now, why would you do that? Because what you end up with if you do that is you end up with an arrow that is still pointing due north, but now has a length of 1. And that result, which we write R with a caret over it, and sidebar, we call the caret a hat in physics because we're losers. So we would read this thing is called R hat, literally. I mean, I know it's really silly, but literally that's the formal name of it. R hat is then a vector. It is a vector. It is an arrow with direction and length. Only what it's designed to be, it's the unit vector for the R vector. It's the unit vector associated with or corresponding to the original vector R. In other words, what R hat is an arrow that is pointing due north, just like R originally was, but it has a length of only 1 now. So it's a vector designed to show the direction of an original vector, but not have the size of the original vector, just have the direction of the original vector and deliberately just having a length of 1 unit. The whole, right? So again, everything that Christopher said. So if it made sense to you when Christopher said it, and just hold on to that. I'm not changing it. I'm just whatever, saying it in different words. So the point is that just like writing R by itself is a way of isolating or focusing our attention on the pure size of the vector R, then from now on, R with a hat above it is a way of isolating the pure direction of the vector R. Like R, the lowercase r with no symbol above it at all, is the pure size, but it's just a number. It has no directionality at all. Whereas R hat has directionality, but it has on purpose a size of 1. If you get it in the end of the day, it allows us with this construction at the end of the day. I'm just going to write one more thing on this page. At the end of the day, if you just multiply both sides by R, it means from here on in, we can think of the vector. I'm going to say, we always think of vectors as quantities that have magnitude and have direction. Now, with this notation, it's just a way of not just saying it in English from now on. From now on, if I think of a vector as something that has magnitude and has direction, I can from now on express that as one mathematical symbolic package. I can literally from now on express any vector R as a literal multiplication, as a product of its pure size multiplied by its pure direction. Like from now on, the vector R is its size times its direction. Well, let me say it one last way. I know I said this a lot yesterday, but the implication here, or the background assumption here, is that when you multiply a vector by a scalar, when you multiply an arrow by a pure number, what you do is you just take that arrow and you scale it up, or you scale it down. You're just stretching or shrinking an arrow when you multiply an arrow by a pure number. That's actually why we call pure magnitudes scalar quantities. They just scale up or scale down vector quantities. So from now on, you can think of any given arrow at all, you think of from now on as an arrow of unit length, an arrow of 1 unit length that's pointing in a certain direction, scaled up or scaled down by a certain size. That's what it means when we say the vector R is a size times a pure direction. So last thing I'm going to say now, and then we're going to see, cool. Oh, cool. Thank you. Thank you, Alana. All right. Which is a good signal for me to stop too. Okay. Sorry. That was 3 minutes ago. All right. But thank you, Alana. Okay. All right. So that's the point of it. So yes. So whenever you see, I'll back to the other page in a second. On this, not well, yes. So like the last equation here at the bottom, which looks very much like an equation you got yesterday, but it's a little different. If you look closely, this last equation at the bottom is something we're going to establish today. It's very similar to something from yesterday, but it's actually a little bit different. You might notice basically it's equation from yesterday, but with one of the q, with the lowercase q, like gone or divided out. We'll talk about that. But if you look at this equation, the left side is a vector. The left side is the what in this case is called the electric field vector. And what it's saying is the electric field vector from here on in is a bunch of gobbledygook, a bunch of numbers, a bunch of constants, all multiplied by each other to make one big number, multiplied by a certain unit vector called the R unit vector. It's basically saying the electric. So anytime you see an equation with an R hat in it, that's a way of telling you, okay, what we have here on the right side is an arrow. The size of the arrow is everything in the parentheses. The direction of the arrow is whatever the direction of some R vector that we must know about somehow, somewhere, whatever the R vector, the displacement pointing from something to something, whatever some known R vector's direction is, that's the direction of this. Bottom line, when you do out the math, as we'll do today, you never, R hat says, don't multiply by me. I'm just there to tell you direction, like Christopher said. I'm just there to tell you direction to complete the vector statement. I have a value of 1, always. Any letter that has a caret on top of it, or what physicists call a hat, any letter that has a hat on top of it has a numerical value of 1. But it's an arrow of length 1 pointing in a certain direction. If it weren't there, the statement on the right would not be complete because the part on the left says we're talking about a vector here. Okay, I think, okay. It was clear 5 minutes ago to Alana, so that's enough. So we're going to see this in action today, but really, again, and maybe if one other person in direct chat, if one other person could even just tell me whether it's clear now or clear now or not still clear in direct chat, just someone that wasn't, just oh, well, that's good. All right, I'll take it. Thank you, Samantha. All right, cool. So I'm going to move on. I'm going to move back to the sheet. So hopefully you guys have the sheet now in front of you. So what I'm going to do is, cool. Thank you, Valentina. Awesome. I'm laughing at myself. I'm not laughing. Yeah. Okay. What I'm going to do now is I'm going to change the view on the screen. I'm going to change view on the screen. I'm going to start talking through the homework sheet. Again, basically, I'll be giving you, I'm not going to necessarily do the 5-step method, but I will be giving you answers, which you are welcome, as long as you understand them, as long as you can convert them into 5-step method. Great. And I'm not going to get through the whole sheet today, but we're going to get somewhere. So I hope you have it in front of you. Again, for anybody who, so bear with me for a second while I switch things around here. Also, I'm just going to put this again in the chat for anybody who just joined. Okay. All right. So I'm switching the view. Okay. Right. Oh, okay. Okay. I believe this is homework number 6. Right. Okay. Okay. So yeah. All right. So on page 2 of that homework sheet of homework 6, it is homework 6. Okay. So what we have here. Okay. All right, so here's the setup, right? We've got this source charge. Capital Q1 is like the big charge. It's got a magnitude of positive 50 coulombs, right? So again, just in terms of yesterday, what that means is we've got like, okay, we've got like 50 times 16 quintillion protons sitting there all jammed together in this like head of a pin space, right? That's what that means. And that is not unrealistic. It's pretty large, but it's not like ridiculous. So they're all sitting there in this space. And then 5 meters away in some particular direction that was not specified here, but in some direction, 5 meters away, there's this other charge sitting there that we're calling Q2, right? And Q2 is what we call the test charge. Now notice this already. Like this language. Notice we always call the big charge we tend to call the capital letter, the big one, the number one, we tend to call it the source charge. And we tend to call the other one, the one that we tend to call the other one, the test charge. And you start to see why, hopefully, during this problem. Like the first idea is that the source is the one that we're regarding as creating the force. Right, where all these questions are going to be about how does the Q1 affect the Q2? How does it pull or push? How strongly does the Q1 pull or push the Q2? So we regard the Q1 as the source of the interaction, the thing that's creating what's going on, kind of like the way we think of the sun as pulling the earth gravitationally, right? But now again, don't ever forget, and that's just the way we're regarding it. That's the way we're focusing on it. At any time that Q1 is pulling on Q2, Newton's third law is operating and multiplication is commutative. So any number that we get for any of these problems that says Q1 is pulling or pushing on Q2 with this number of newtons, it's absolutely also true that Q2 is doing the same thing to Q1. It's just that in the opposite direction. It's just that's not what we're focusing on in any individual question. So we regard Q1 as the source. And notice we regard Q2 as the test. We could have called the Q2 like the receiver. Like that would be sort of like the way we could have. But we tend to call it the test because, as you'll see throughout this problem, it's Q2 that we keep playing with. We're sort of testing out. We remove the Q2, the 3 coulombs after exercise 1, and we put in a different one in exercise 2, et cetera. And we keep getting different answers because what we're sort of doing in our heads, we're kind of, we're doing, speaking of our heads, we're doing an experiment to kind of test out the ultimate effect of Q1 on its surrounding neighborhood, right? So it's kind of like Q1's kind of like an independent variable, you could say, and Q2 is kind of dependent or something. So we call Q2 the test. Anyway, the first question asks us, what is the electrostatic force exerted by Q1 on Q2? It gives us all the numbers. So this is a pure plugin, as I'm sure you noted. And in fact, so we're going to plug in, and it's just asking about magnitude, I believe. Well, all right, no, it's actually asking for the force, but let's focus on magnitude first. Well, either way, okay. It's asking for the force. So the force is K E Q1 Q2 over R squared times R hat. And we go to the next page now. I'm just rewriting it, the same thing. And it's plus or minus, we'll find out in a second which one. Okay, so we're just plugging in, right? But I'm not gonna plug through every single one of these exercises, obviously, but I'm gonna walk slightly carefully through the first one, just so we're all on the same page. First I plug in the K constant. Now I told you yesterday that K is, I'm sorry. Yeah, I'm listening, or sort of, actually I'm not, wait a minute, I'm not listening, hold on a second. Let me just get this. I'm just gonna write this first. Okay, yes, Chris, defer.
No, you can go.
Are you sure?
I was about to say what K is. It's cool though.
Oh, okay. Well,
no. It's cool.
Okay, sorry. No, it is better coming from you than from me. I shouldn't. All right, but yes, that is okay. So, but did I say in the sheet somewhere? I'm looking. Did I point out in the sheet that this is a number that? Did I?
Did you have it in the beginning saying what K is?
Okay. So I want to say a couple things about that. All right. So I do say what it is. I'm going to say 2 things to everybody right now. First of all, I mean, it's a huge number. I keep saying you don't have to memorize it, but you do have to understand that it's enormous, especially compared to the gravitational constant. Also, if I ever asked you what the units were, that I would expect everybody to be able, you get what's going on if you can say the units for this thing, because meter squared have to cancel out with the R squared in the denominator, Coulomb squared have to cancel out with the Q's in the numerator, and then you have to be left with newtons to make a force, right? So that's the number. But let me say 2 more things about it, one of which I do say in the sheet. One thing is, there's another traditional way that we express this constant, which I need to tell you right now. As it says in the sheet, we often write this constant as, in fact, a combination of other constants. This is bizarrely important, everybody. It says in the sheet, but I haven't said anything about this yet, so bear with me. Often, instead of writing K sub E, which is kind of annoying because we already have so many Ks anyway, we often write 1 over 4 times pi times this new number that we've never mentioned before, this new other constant. And this constant, which is technically called the permittivity of free space, I'll write that in a second, but this constant is 8.85 times 10 to the negative 12th Coulomb squared over newtons times meter squared. Now, again, you don't have to memorize that number. But it is, if you ever wanted to look it up on Google or whatever, and we will see it for the rest of this class, it is called the permittivity of free space. I'll explain that by the end of the class. Okay, it's just a number like Planck's constant or anything else. It's a constant that expresses an aspect of the universe, a universal aspect of the universe. It expresses sort of how transparent free space is, like as opposed to glass, how easy it is for light to get through free space. It's a indication of that. Like glass has a different number, water has a different number. All translucent media have slightly different permittivity constants, just like that's what it's about. And if we were measuring in certain units if we were measuring in certain other units, then this number would just be called 1, because there's nothing more permissive. There's nothing more transparent than free space. But because we're trying to stay in metric units, like all of our numbers get funky. So this is a very funky number. You don't have to memorize it. What you have to notice is that this number is very tiny, not coincidentally, because we're defining this number so that if you put it under 1, well, first, if you multiply it by pi, and then you multiply it by 4, and then you put the whole thing under 1, then you get the k number. So this number would have to be tiny if it's in the denominator of a fraction that produces a huge number, right? Now, why we do this, you will soon see. I'm not trying to hold you in suspense right now, but it's a little bit of Monday. It's a little bit of like, it's kind of like the omega squared thing in differential equations. Like it will make sense once we've done a couple of other things, but for right now, it's a notational idea that from now on, let me back up. I originally wrote k as k so that you could really clearly see how similar this equation is to the gravitation equation. But now that you see that, both equations are an inverse squared law equation that have one constant at the beginning, from here on in, I'm going to write this constant as a combination of 3 other constants. You will see why very shortly. But from now on, I'm going to do that. They're both equivalent. They come to the same thing. They come, if you like trying on your calculator to do this 8.85 times 10 to the negative 12 times pi times 4, and you put the whole thing under 1, you'll get 8.99 times 10 to the 9. Okay. So that's number 1. I just want to make that clear. It's like super annoying at the moment. It's just a notational thing, but it does provide a great amount of convenience in a couple of beats from now. The other thing I want to say, but so we're still going to use this number, this 8.99. Just note also, all right, so this is note 1 is all of this. And note 2, sometimes, just like gravity, lowercase g is 9.8, and often it's convenient to just round that to 10, depending on the context, if you're not in the lab. Same thing here, like if 1 over 4 pi epsilon naught is approximately 8.99 times 10 to the 9th Newton meter squared divided by Coulomb squared. And if we're rounding anyway, if we're chopping off digits anyway, you can often round that and say that that's like 9 times 10 to the 9th. And then if you really want to be crazy, sometimes, like maybe on an exam, for example, where the numbers get annoying, you could even sometimes say, well, 9 times 10 to the 9th is basically 10 times 10 to the 9th, which is 1 times 10 to the 10. Sometimes I will do that. I'm alerting you to the fact that sometimes I won't do it without telling you, but we can round that number sometimes to just, in other words, to 10 billion. And that will happen on the web or like other textbooks that you check sometimes. So don't be thrown if someone ever writes it that way. It's like writing gravity, lowercase g as 10. Okay. It's just so much easier to work with. Okay. Having said all that, in fact, maybe I'll do that now. Well, I won't do it first because you probably didn't do it. But all right. So going back to the exercise, we are trying to figure out this. So all we're doing is plugging into the equation one time, and I'm not going to put the units in for a second because it's going to get all messy. But so we said, all right, 50 times 3 all over, and the distance was 5, right? So it's all over 5 squared, right? So, I mean, well, I'll do it. Actually, I will do. I'm going to do it my way, and we're going to compare it to your numbers. So I'm going to just is that a chat? Okay, I'm going to round. I'm going to say that's basically 1 times 10 to the 10th times 50 times 3 all over 25. See, if I round like that, I can practically do this without a calculator, right? And even if it's not going to be exactly the same answer as yours, he'll be close enough, you'll be able to see whether you're right or wrong. Oh, hello. So I have 150 over 25, right? In other words, this is so in other words, I have this. The more you can do stuff in your own without a calculator, the more you get a feel for the numbers and the more you can trust your own work. Because like, I think that goes in 6 times, right? So I'm getting something like, now watch this. Probably I made a hideous error and everyone's going to laugh at me and I'm going to be fired. But I believe, you tell me now, this is what I would say my answer is. Let's back. So did you get something like 5 point something times 10 to the 10th newtons? You got, or I'm looking at the chat. Wait, I'm going back to the chat. Oh, awesome. Okay, awesome. Wait, I'm looking at the chat. I see at least one thing. Oh, yes, I see a yes and a 5.39. Okay, awesome. So I rounded up severely, right? So first of all, your answer is more accurate. This is, you notice I'm saying approximately equal. If you got like 5.4, like Valentina and Juliana, if you got like 5.4 times 10 to the 10th, you're more right than I am, if you want to say that. But my quick check is verifying that we're all in the same ballpark. We should be getting something in the neighborhood of 660 billion newtons pointing in the R direction. Like, I should be very specific. Like, my answer for the force vector is a force that has a magnitude of 60 billion newtons pointing toward, like, what does the R hat mean in this case? To go all the way back to Alana's original question, R hat is in my final answer because the final question asked for what's the force, and force is a vector. So here's my force vector. It has a size of approximately 60 billion newtons, and it's pointing, like, it says plus, it has a plus sign in front of it, and then it has an R hat at the end. So what that means is it is literally pointing in the same direction as the original R vector. What's the original R vector? It's the vector that pointed from Q1 to Q2, like this R vector right here. So my answer is saying we've got a force that's pushing along that displacement line. The force is pushing, well, the force is directed from Q1 to Q2. Let me say as clearly as or for the 85th time, that the reason a lot of people don't get this whole R hat thing after a while is because it always sounds like I'm saying something obvious. It sounds like I'm saying something that you don't even need the R hat to know. Like, it sounds like I'm saying something that you already knew, but we're not exactly. We're saying that the force is directed from Q1 to Q2, as opposed, which means it's a push, as opposed to a force that's directed from Q2 to Q1, which would be a pull, right? So first and foremost, this R vector is there. I mean, this R hat thing is there to tell us whether it's along the line of displacement or against the line of displacement. But let me also say now, as a foreshadow, for those of you who are still like, okay, I get it, but really 2 days on this, Yaverbaum? Like, for any of you who is like, I get it now, but that's like stupid. Like, why are we spending so much time on this? Which is a fair critique. Let me tell you that when we get to the next force called the magnetic force, it turns out the magnetic force is based on the magnetic force from one charge onto another charge is based on the line that can be drawn from one charge to the other. But the magnetic force is not directed along nor against that line. It turns out the magnetic force, I mean, this is a big foreshadow here, I'm sidebar, but just so you know, there is no law of nature that says all forces have to be directed anywhere on the line that connects one thingy thing to another thingy thing. It turns out some forces actually act completely off kilter. There's some things called magnetic pushes and magnetic pulls, which actually do not go from me to you, but go to the side. So just saying, we're going to get to that. But just so you know, the reason we focus so much on this line between the two objects is because that is a line of reference and a lot of things happen on it and a lot of things do not happen on it. It's not actually obvious that any force would have to be directed along that line at all. But it turns out the gravitational force it always pulls in along that line, and the electrostatic force is either in against that line or out along that line. Anyway, so, okay, that's my numerical answer. My answer is that at the bottom page. Can I just get one more person in the chat besides Juliana or Valentina? Can anybody else confirm or deny that they got any kind of answer anywhere near what Juliana or, okay, cool. All right, that's good enough for me. Okay, great. Okay, awesome. Woohoo. Okay. Yowza. All right. All of you. Well, actually, I'm gonna. Oh, thank you. You're so nice, all of you. So I'm just gonna say it quick. So thank you, Michaela. Thank you, Bree. Thank you, Dante. Thank you, Allison. Thank you, Toiba. Thank you, Key. Okay, sweet. All right, now we're gonna move on a little faster. Now it's 4:51. We're gonna go to the next one. But that's the answer to that one, right? And you should have a diagram if you're doing it out, for homework and all that. And you, I think I included the steps, but I didn't label them. But you should. Blah blah blah. Let me just go to the next. So the next question now. I keep messing up my colors. The next question, all is the same, except for we change the test charge, right? That's why we call it the test charge. So again, we have Q1 is 50. And it's separated by displacement R from Q2. Okay, but now Q2 is -6 coulombs. Okay, so and again, the equation is the same. I'm going to start writing it this way. So from now on, I'm writing it this way. It's the same equation, right? Just get used to the fact that I'm now writing that whole constant in that funny way. Okay, so here's the equation now. Now, I could bore the bejeebers out of all of us again, and I could walk through that whole plugin. And I'm hoping, by the way, if anybody did have a question or confusion, if you have a question, please put in. Just because I'm making it sound like, or maybe some people are making it sound like it's obvious, does not mean it's obvious to everybody. So if you have a question, put it in the chat. No shame, no gain. But now this next one, assuming we did all follow that plugin, I could do the same old plugin all again from the start and plug in numbers. However, I might notice something that some of you might have noticed. Like I might be able to save a little time here, which actually is the intention of this next question. Maybe I could just make like an adjustment and get the answer faster. Is there anybody, especially someone new, like maybe with all respect, maybe not Christopher or not Alana or not, is there someone new who maybe wants to suggest even privately in the chat something? Oh, looks like something's there. Something that they did. Oh, did I not? Wait a minute. Oh, sorry. Hold on. There's something in the chat that's not that way. Did I? Yeah. So we do. Wait, did I not write the? So we do write the answers with the R hat. The R hat is part of the answer, but it's just left. So, sorry. So someone's asking in the direct chat. So are we going to write the answer with the R hat? And I'm not sure if they put that in before I wrote the answer or not. But yeah, our answer, if they just ask for force, our answer should include the R hat in the answer. But there's nothing more we do with the R hat. It's just sitting there and it's telling us. Basically, the R hat is giving us information, especially if you take the R hat along with the positive sign together, what they mean. Sorry, I don't want to do that. Together, they tell us the positive sign with the R hat tells us that the force vector points in the same direction as the displacement vector. I'm going to say this one, and maybe direct chat person who's asking me that. It's again, anything about R hat is, if anybody wants to ask anything at any time about R hat, it's fair game because it's important and it's new. But so let me say this a totally different way for everybody. Please notice what we're really saying. When we compute this force vector, we're really saying that we take a pre-existing vector, a displacement vector. We take the displacement vector, we shrink it down to a size of 1. Then we scale it up according to Q1 and Q2 and the constant. Like we take a displacement measured in meters, we shrink it down to 1. So we're just looking at this little arrow pointing in a certain direction in meters. Then we scale it up according to the charge coulombs and in the constant, all that. And so we scale it all up. And so we get a new vector that's measured in newtons, what we're saying is the force vector is an arrow measured in newtons that was built from a displacement vector measured in meters. We built a force vector from a displacement vector, and both of them have two different sizes, and but the direction of one is heavily based on the direction of the other. It's like either exactly the same or it's the flip. So the positive times the unit vector is telling us the force points from source to test. The positive with the R hat, I know I've said it before, but I'm just saying that it is part of our answer. It's telling us that this final answer is a push rather than a pull. I don't, direct chat person who's asked me, maybe, okay, cool. Great, thank you. I love you, and submit both those for points, please. Okay, all right. So now I'm going on to the next question. And I'll tell you right now, like the directionality, the R hat's going to be the same deal again. But this time I could see right now, this time we're going to be multiplying a negative times a positive. So we're going to have a negative in our answer at the end here. So at the end of the day, our answer is going to be negative blah, 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 times R hat. So at the end of the day, we're going to get a pull this time. We're going to get attraction rather than repulsion, as I think you would get. Okay, wait, cool. No, I'm glad I'm getting these questions just to clarify. Hold on, something in the chat. Oh. Whoa, wait, this is a great question. Okay, this is I'm going to tell you right now, this is a great question, even though I'm going to say that the answer is no, but it's a great question. So the question in direct chat here is, just to clarify, if your answer is negative, does that mean that the test charge is pulling more than the source is pushing? I want everybody to think about that for a second, because that is a great, it's a great question. It doesn't matter what my answer is. It's a great question. I'm going to say it again. I want everybody to think about that and think what you think the answer is. Here he is saying, if it is negative, if the final answer is negative, does that mean that the test charge is pulling more strongly than the source is pushing? Now, let me just say, because I don't want to get bogged down, I love that. I mean, that's a really thoughtful question. I'm going to say right now, no, the answer is no. It doesn't mean that, but let me explain. If the final answer, let me back up. If the final answer is positive, what it means is that the source is pushing a certain amount. And by Newton's third law, that means the test is also pushing that same amount. But push is in opposite directions for both of them. Like if we get a positive, it means it's a push. But go back to mechanics or anything else, even if these weren't charges, if I push you, you push me back automatically, even if you don't try. Even if you're a wall and I push you, you're a wall, I push a wall, what happens? I fly backwards, right? The wall pushes me back. If push means away and pull means toward, then whenever I push anything, it pushes me with the exact same strength. Now, if I push a wall, I go flying. So you might think, well, wait a minute, when he pushes a wall, like it seems like the wall pushes him a lot because he goes flying, and it seems like nothing happens to the wall because the wall just sits there. Well, don't forget, F net equals MA. I'm a wall is a lot more massive than I am. I have a very small mass compared to a wall. So if I push with a certain number of newtons against the wall and the wall pushes me back with the same newtons, because my M is so tiny, my A is going to be huge. So I A big time that way. I'm only going to A the wall a tiny bit, but there will be like, but if I do it hard enough, you'll see a little dent in the wall or something, like, you know, there will be something or a mark. But I'm saying, to go back to Newton's third law, whenever I push something, it pushes me back. And if I pull, if you're on a string and I pull you, then you pull back. And if nothing else, I experience that as resistance, right? Like you don't make it easy for me to pull. So now with these charges, if the sign is positive, that means the source is pushing the test, but it also actually means the test is pushing the source. They're both pushing each other with the same amount of force. Just one will accelerate maybe more than the other. Like the bigger one won't budge as much. That's why we think of it as a source. We always like focus on what the big one is doing because it won't be affected as much by the same force. But if the big one is if the source is pushing the test, then the test is necessarily pushing the source with the same amount. Similarly, on your fantastic question, and I am not, I hope everybody can tell, I am not being, just because I'm saying that the answer is no, it's a very, very revealing question. When you ask, you direct chat person, when you say, if it's negative, does that mean the test is pulling more than the source? No, what it means is, if it's negative, it means the source is pulling the test and the test is pulling the source, and they're both pulling the exact same amount. If I push you, you have to push me back. If I pull you, you have to pull me back. If it's a push or a pull, it's definitely symmetric in both directions. What it means, but I think what you're getting at, direct chat person, is if it's negative, what that means is that one of these charges was negative and the other was positive. So they attracted. And if it's positive, it means they were both positive or they were both negative. So they repelled. There will be contests that we'll look at. There are contests that happen like, is this thing bigger than that thing? But so you're very right to think about, like, is something winning a contest somehow? But here there is no contest, actually. Whatever's happening in terms of forces is a tie necessarily. We're just focusing all our attention on what the source is doing to the test. I don't know if that, I would love it if the direct chat person, okay, wait, I'm looking at that. Yeah, exactly, right. So the negative value kind of means that the two charges would, if everything else were equal, if nothing else was happening, if you get negative, it means the two charges will get closer to each other, yes. And if they're positive, they would get farther from each other. If all other things were yes, got it, great, awesome, great dialogue. I love this class, yada, yada. Okay, no, seriously, that's great. Okay, so now back here, then back to this problem. I'm going to ask if there's anybody else in direct chat or public chat who hasn't said something yet. Did anybody come up with any kind of trick or shortcut for not having to, we could plug in all the numbers again. We totally could, and we'll get the right answer. There's nothing wrong with that. And if you did that, that's great. But is there anybody that saw any faster way to do this? Maybe. And I'm ideally, I guess I am targeting this question to people that have not said anything yet. Or just, and you could do it in direct chat. And if you did say something already, I guess that's fine too, but put in direct chat to get other people a chance. But I'm going to pause for a second. I'm looking, okay, I'm just going to electronically raise your hand if you hear the question. The question is, going back now to part two. Oh, cool. Oh, okay. Those sounds are, cool. Oh, cool. Okay. Awesome. All right. I see a lot of hands now, and I'm seeing things in direct chat. That sound is so bizarrely satisfying. I think that's a new thing in Zoom. Or maybe you guys are plugging those sounds. I don't know, but okay, awesome. Thank you guys. And I see something in direct chat. I'm going to wait till maybe one more person could put. There's one person in direct chat if one more person puts anything. Oh, okay, that's fair. That's fair. That's totally honest. Like tried but couldn't figure it out. Fine, that works for me. I mean, you're totally communicating with me. Okay. Right. There. Okay. Hold on one second. Okay, cool. All right, so I got some answers in the direct chat, and I got some answers. So okay, I'm not going to say it my way, but some people in the direct chat clearly do understand the question, and some people even, I think, did something. And you can put your hands down now if you want, unless you're asking a question. Here's what I'm saying. If you notice, right? Notice F, the force.
Should there be that on the R?
Yes, absolutely. Thank you. Excellent. Please submit that for points. Yes, absolutely. And then by the time I get to the bottom, I'm even at the bottom to simplify this whole thing. I'm just writing the magnitude. No, you're absolutely right. And then at the bottom, I'm saying if we just think of magnitudes, this is a good symbol to know if you don't know the symbol already. Like if I write alpha like that or that squiggly thing, that means directly proportional to, and you know in math what directly proportional, if I say F is directly proportional to Q2, what I mean is F equals some constant times Q2, right? I mean that I could put F on the y-axis and plot Q2 on the x-axis, and I would get a straight line, right? That's what it means to, and it's true, right? F, the magnitude of the force, equals some constant times Q2. It's a linear relationship. Now, why am I bringing that up? Well, I'm bringing that up because, as at least one person in the chat told me, so to change from test case, to change from test case number 1 to test case number 2, all we did, we changed Q2 from Q2 equals, equals, I don't even remember now. I think it was 3. Was it 3? Yeah. To the new Q2 equals -6. I believe that's what we did. I don't even remember. Hold on. I can't even. Yeah, okay, right. So all we did, i.e., we multiplied Q2 by -2, right? That's the only change we made in this whole situation is we swapped out a positive 3 coulomb test charge and we subbed in a -6 coulomb test charge. All we changed is we multiplied the test charge in effect by -2 coulombs, or by a magnitude of -2, right? If we really believe that like, I don't want to make this more I don't want to make this more mathematical than I have to, but really, if you really believe in direct proportionality, I'm losing the Zoom. If you really believe, yes. Can I go back for a second? Yes. Sorry. Okay. I'll keep talking now. This is one of these moments where I'm probably making this more technical than I need to, but like, if they're really if one is directly proportional to the other, then that means if you put them on a graph, you'd have a straight line, which would be cool. Thanks. That means the slope would be constant. That means that that means if you double the independent variable, necessarily you double the dependent variable. I mean, that's literally what direct proportionality means. Whatever you do to one side of the equation, you do to the other side of the equation. So if we literally just multiplied Q2 by a value of -2, it does seem to me thus, if part 1, our answer, now I'm just talking about magnitudes now, right? Well, no, I guess I'm not. Okay. If part 1, I'll give myself more room. If in part 1, our answer was approximately 6, I think it was 6, times 10 to the 10th newtons. Make it more clear. Times r hat. I believe that was our answer for, yeah, +6 times 10 to the 10th newtons times r hat. If that was our answer for part 1, then our answer for part 2 should be -2 times, let's call that answer F sub 1. Like, it should just be -2 times our answer from number 1. i.e. it should be F should equal negative 12 times 10 to the 10th newtons times r hat, which, if you want to express it properly in scientific notation, is negative 1.2 times 10 to the 11th newtons. Why is my handwriting hideous? Okay, I'll rewrite this just because the final answer to all these things is always the most illegible, and that's not fair to anybody. So I'm saying it should be negative. I'm saying F for answer 2 should be negative 12 times 10 to the 10th newtons times r hat, which written properly is negative 1.2 times 10 to the 11th newtons times r hat. So first of all, let me say that's my answer. Now, again, that's my answer based on that's an approximate answer. You probably get, maybe you could tell me in the chat, you didn't get exactly the answer because you're being more exact than I am. And that's fine. And I will tell you that if this were an exam, you could do it your way or my way. We both have advantages. My way, like I can keep a feel for the numbers as I'm going and whatever. You should tell me, I'm expecting, in other words, that even if you didn't round, and even if you didn't see this trick, if I'm doing things correctly, your answer should be something like in the 10 to the 11th order of magnitude. So maybe tell me in the chat if it is. Yes. Okay. Thank you, Michaela. Awesome. Awesome. Okay. Yeah. And thank you, Julian. Oh, I mean, thank you, people. Thank you, Valentina. And thank you, direct chat people with your falsettos. Yeah. Okay, so cool. So we're all getting the same answer. Now, there's a couple important things here. First of all, I know it's clunky with the R hats. The R hats are the new thing. Just again, note this answer I'm getting an answer for a force. I'm saying the force is newtons times R hat. Newtons is the size, right? Forces should have a size, and that size should correspond to newtons. Like this is an actual force. It's a very, very large force, I might add. I mean, this is a huge force. You know, this is like 12, excuse me, this is like 120 billion newtons. I mean, that's very strong, but that's a real number. But then, so there's this number with newtons and then multiplied by R hat. What's going on there? Well, R hat, remember, doesn't change the units. R hat doesn't have any units of measurement, and R hat doesn't have any size. It's just an arrow of size 1 pointing in a certain direction. So the direction from Q1 to Q2. So what this whole answer is saying in the end is we have this enormous force that would be pointing from Q1 to Q2, but there's a negative sign on it because, in fact, Q2 was an electron in this case, or a bunch of electrons. So the whole force isn't directed from Q1 to Q2. It's directed back toward Q1. Yes. Hold on a second. Yes, I will be done when you get back. Have a great.
Why is there two cars?
Because we're
Why are we right?
for a couple of days. Yes, yes. I love you. Have a great time. I'm totally jelly. I'm totally jelly.
Wait, will you be done when we
Yes,
get back?
I will be-
At 9?
Yes.
Can I use Nikazan?
Yes, you can look on the Kazan.
Once again, don't listen to anything he
All right,
says,
that's great. Okay. Okay.
or you'll be dumb, just like him.
All right. Thank you.
Live child.
Okay. But now you. Okay. I love you. Have a great time. I'm very jelly.
Yeah.
Say hello. Take
Right.
pictures for me.
Right, Felix is better than Daniel in the chat.
I think we're all clear on that. Yes. Okay. Did I mention about having to? Okay. Am I? And we just paused for a public service argument for contraception. Okay. I did not say that. Oh, yes, I did. Okay. And I don't mean it, but I did say it. Okay. You ever notice that the word awkward is itself a very awkward word? I mean, it's like W's and K's everywhere. Okay. So that's the answer. That's the answer. What else am I trying to say? Oh, so it's a pull, not a push. The R hat is there to say, this is a vector. It has a direction. The direction is from Q2 to Q1. Okay, that's number one. But number two now, we're going to go faster and faster now, obviously. Number two do you see, well, I'm going to pause and ask, whether you did it or not, doesn't matter. And if this were on an exam and you did it your way, it'd be fine. But can you just raise your hand if you see what I did and why it's okay, like why it worked? Cool. Thank you, Michaela. Thank you. Is it cool? Cool. Thank you. Thank you. Okay. Awesome. Okay. Because great. And so now I'm going to start. I'm in fact going to ask you for the future answers now, or for a bit. Like, okay, I'm going to go a little bit faster now. This is ultimately to make a point. If we now go, I'm going to just cut to the chase for number 3. If we now go to number 3, say I'm really excited and I just did this trick, right? And I feel like I saved myself a little time, even though I talked about it a lot. Then I get to number 3 and I'm like, all right, so I'm going to do the trick again. Well, what did we do now? We like took the old charge and we like multiplied it by -5/6 or something. Or we could even say I took my original charge and I multiplied it by +3/5 or 5/3. So if I want to continue my trick, what I could say is go back to my old answer and multiply it by like 5/3 or 3/5 or 5/6 or something. But if you're anything like me, the minute even as I'm saying that, I'm like, ugh, that's kind of a clunky. Like, that's just annoying enough that I'm not really sure it's worth it. Maybe I'll just plug it. Like, I'm going to get bogged down in whether it's 5/3 or 3/5 or what. I don't even know what. And once I have to multiply by a fraction, I mean, I might as well just. So on number 3, I'm not even sure my trick is that great. And that's on purpose. I'm trying to show you. So on number 3,
Wait.
oh, sorry. Yeah, I'm sorry. Go. Yeah.
Would it make more sense to, because further down they ask you for, you emphasize do not, you said do the next in any order. I think it would be best to do in number 4 first, when we can find 1. And if we have 1, we can basically go to any number we want.
Boom. Yes. We could, yes, I'm not being sarcastic. Yes, that is awesome. That is exactly the point. And okay, so let's just do that. I'm going to do what Chris and that is the purpose of this whole thing. This is called like edumacation, because I totally agree with him. The problem is designed to be just annoying enough to get you to kind of see that on you, or at least to get Chris or anybody. And there was at least one person in direct chat. Like the problem is just annoying enough and just broken up enough that Chris on his own is like, really? Like, there's got to be, screw this. I want to go, I'm going to do number 4 first. And yes, let's totally do that. I agree. And yes. So yes. So number 4, it says, let's go back and just but see, honestly, to everybody, if I just asked you number 4 first, which I could, I don't know that we would appreciate, well, you be the judge, but it seems to me we can appreciate the purpose of number 4 once we're spending a little time that we want to now save. Okay, I won't justify it to you, but I feel like now I appreciate this all the more, especially because Chris said it, not me. Christopher said it, not me. Like, we could say, all right, what is the force that is generated by this situation when Q2 is 1. In other words, what Christopher is saying, let me be more clear. I'm sorry. When Q2, when the test charge is literally +1 coulomb, what Christopher is suggesting is if we now jump to that, and again, somebody else in the direct chat also, I want to give her or him total credit. Someone else also saw this. But if we jump to that, and figure it out. Oh, and notice this too. If we do what Christopher's saying, if we jump, sorry. Okay, I'm sorry. Yeah, I don't know why I do. Okay, thank you. I guess I was waiting for permission because I don't know. Okay, great, thank you. Okay, notice this now with the thing that Chris is saying, like specifically what I'm now plugging in the numbers. I'm plugging in numbers to find out what the force would be exerted by this 50 Coulomb positive point source, I'm finding out what it would exert at a certain displacement, at a displacement of 5, at a distance of 5 from a positive 1 Coulomb test charge. In other words, I'm emphasizing right now, we're figuring out what the value, what we would get in the end of the day on a 1 Coulomb test charge, but we're figuring it out holding the source value and the distance as fixed inputs, right? So if we figure this out now, so we have 1 times 10 to the 10th times 20, times 2. Yeah, this is the thing that someone said in the direct chat like 10 minutes ago, and it was awesome. Right, because 50 divided by 25 is 2. Right, so we get approximately 2 times 10 to the 10th, positive 2 times 10 to the 10th newtons times r hat. Now this, let's be very careful here. This answer, okay, so this is approximately the answer to 4. Again, your numbers might be more precise if, like, if you weren't rounding the way I am. But this would be the answer to number 4. And then there's a major purpose of this. Chris intentionally skipped 3 and did 4 first. Because what he's saying, I mean, he's agreeing, like, if I try to do the trick that I already did and just sort of like, it's like too annoying. But he's basically saying, look, if we get a base value first, if we get what the force is acting on a 1 unit test charge, then from here on in, anybody could name any test charge they want, and all we got to do is multiply the test charge that they give us by this number that we just got. In other words, if we go back to 3 now, since we were allowed to go in any order we want, if the test charge, if Q2 is equal to positive 5 coulombs, according to the Chris and One Direct Chat person strategy, literally the answer here, then the answer would literally be, plus 2 times 10 to the 10th times the 5. Like, you, right? I mean, that's what we're saying. That if what we just got was the amount of force exerted on every or any 1 coulomb of charge, then if 5 coulombs of charge are sitting there, then they're going to receive a force that is 5 times as great. It's all about the direct proportionality between force and charge. So we would get for answer 3, we would get, and this is all approximate, but we would get approximately 10 times 10 to the 10th, which is 1 times 10 to the 11th newtons times r hat. And it would be positive because we multiplied it by positive, right? And then finally, if we go, just to complete the exercises, if we go to number 5, hopefully you see it's clear. If we go to 5, then here, like, Q2 is now -2. So we would just take, again, that base result that we got and multiply it by -2. So F would be -2 times the base result, which was 2 times 10 to the 10. Which equals -4. So, but now, there's a negative sign involved now. So we get -4 times 10 to the 10th newtons times r hat. And that would be our answer for 5. So first of all, these are the answers. These are approximately the answers. But now, okay. So now the sheet tries to tell you why we just went through all that. Partly just to practice the equation, sure. To do these plug and chugs, sure. But now I want everybody to realize the thing that Chris and one other person realized, and I'm well aware that others of you probably realize it too. And you're welcome at any time. Look, literally, if you just put in the chat right now, I also realize that. I just didn't say anything. Like, what am I not going to believe you? I mean, you could lie, I suppose, but I hope I'm saying, feel free to let me know if you didn't realize it, but now you get it, or whatever. It will help me teach at the correct pace for you. But this is a big point because it's not just a mathematical trick, okay? This also gets at why we call that second charge the test. Because what we're saying from now on, from here on in, and here comes like an equation from the front of this whole PDF, from here on in, let from here on in, we're going to use a capital E to mean electrostatic field. And this is the first time we're introducing a very important notion in physics called a field, okay? A field is a very big, I'm sure you've heard of fields like in life. They're a very important concept in physics. They're a very simple concept in a way, but they're definitely not an easy concept. They're a very abstract concept. A field is a very, very unthingy thing. Okay, there's a number of different ways to think about a field. Let's first start with what we just saw. First and foremost, mathematically speaking, a field is just net force per charge, like what I just wrote here at the bottom. Okay, and I think it says in the sheet. I mean, there's different ways to say this, but first and foremost, the field, the electrostatic field generated by capital Q1, the field is the vector that we get when we multiply all the appropriate numbers and we input all the appropriate information, except we act as though it's all being exerted on a receiver of positive 1 unit charge. You know, right? That's what we just did, right? In other words, the Chris trick, like the field is all of those values put together, except what treating the test charge or acting as if the receiving charge is literally a positive, always positive 1 coulomb of charge. So partly mathematically, we're doing that so that we have a package of all the, what we're really doing when we make this calculation, when we skip to number 4 and we do that trick and we get when, in other words, when we in number 4 got that the force when we decided that the force for a 1 unit of charge, when we decided in number 4 that the force being exerted by Q1 onto a test charge of 1 coulomb was 20 billion newtons, what we were really saying is we're saying that for each 1 coulomb that could be located 5 meters away from the 50, right? What we're really saying is for any and every 1 positive coulomb of charge that could be sitting there at that location at 5 meters away from a 50 coulomb source charge, for every 1 coulomb that could be sitting at that location ready to receive a force, every 1 coulomb receives this force of 20 billion newtons, right? That's what we're saying. We're, in a way, what we're saying is we got a package of it. We're that number, the number at the bottom of my sheet, 2 times 10 to the 10th newtons, right? What is that? That's how strongly our source charge is pushing on to any and every 1 unit of charge located 5 meters away. We're literally saying, so if you put 2 coulombs of charge, then each one of them will receive this force. So the total force will be, 4 times 10 to the 10th. If you put 3 over there, the total force will be 6 times 10 to the 10th. But we're literally saying this is what our source is doing to any and every 1 unit of positive charge that could be at that location ready to receive. So what we're saying is this is the force waiting to happen. This is this bundle of information that we just got. Like, first of all, it makes our math easy. Like Chris and everybody just did. We're saying from here on in, if you ever want to know what the force is happening over here, 5 meters away from this 50, well, we got a number ready to go. There's a number sitting there. There's a number of newtons sitting there, like ready to push. 2 times 10 to the 10th newtons is ready to push on every 1 coulomb that might ever be deposited at this location. So the minute we deposit a bunch of coulombs at that location, each one of them receives this force, and it creates a total force of this number times the total amount of Q2. In other words, partly what I'm saying is purely mathematical. I'm saying from now on, that force per charge that we just calculated in part 4, partly we calculated just to make our math easy from now on. But it's not just making our math easy, it's like a prediction. We're saying that bundle, that force per charge, we're going to call it a field from now on. We're going to say that from now on, if you ever want to know the net electrostatic force at a given location, right? Well, as long as you know the field at that location, just multiply the field at that location by whatever amount of test charge is sitting there, right? I'm just flipping. I'm saying I'm defining field to be net force per charge, net electrostatic force per charge. And then I'm just kind of like I did with the vectors before. I'm defining it that way so that from here on for the rest of my life, if I want to know how much force is acting on a test, on a receiver, if I want to know how much force is acting on some bit of charge somewhere in the universe, I'm saying, well, as long as I know what the field is there, as long as I know what force is waiting to happen, as long as I know what big source is in the neighborhood and how far away it is, as long as I know the information bundle created by that source at some distance away, as long as I have that information bundle, call it a field, then that's basically what I need to know. The field is there, ready to go. I put some charge, lowercase q, lowercase q2, if you want to call it whatever, put it there, multiply the two together. That's the force acting on the Q2. So I'm going to pause for a second to say a couple. So what I'm saying is in English, first of all, in English. So this means electrostatic field. So E from now on stands for electrostatic field. What it means approximately is net electrostatic force per charge. I mean, again, that's like what we just sort of constructed with this math. But what it also means is, or what it therefore means is all information, all identifying regarding force and location bundled together into a vector. Okay, I'm going to say more. But I'm saying, well, how do you think? So here's what a field is from now on. In a way, a field is a force it's a force per charge, mathematically, and that's all it is. But let me say again, in the case, well, I mean, mathematically, it's literally the force divided by Q2. So it's all of the symbols in our force equation except for the Q2. Like we're just treating Q2 as one, right? So mathematically, it's very simple. It's literally take that whole force that you calculate, divide out the Q2. That's your field. What does it mean? What it means is the net electrostatic force, like per unit charge, you could say per unit charge, per unit test charge, even we could say, I suppose. But what does that mean? Or what's the point per unit test charge? But what the point is that from here on in, we start thinking of things this way. We think of the field as a bundle of information. It's all the information describing how big the source is, like the magnitude of the source charge, or if we were talking about gravity, it would be the magnitude of the source mass, right? It's the size of the thing creating the force. It's the distance away that the thing creating the force is. So it's that information bundled together appropriately, like 1 divided by the other squared, times the appropriate universal constant. So it's all this information bundled together and then multiplied by a unit vector. So it's this arrow. It's this bundled together into a vector. It's a vector sitting there at a certain location, at a certain location called R away from the source. It's this little arrow sitting there that's telling us what the whole impact of the source is on the universe. And so another way I could put it then is what it is the force vector waiting to happen, if you like. Now, why do I say waiting? So I'm saying one way to think about a field, which is what we're introducing here for the first time. I mean, again, you've probably heard of them your whole life or in other classes or maybe even in lab, but here's my presentation of what a field is. A field vector is a force vector waiting to happen. A field vector exists at a given location. It is the force vector that's waiting to happen at that given location. Why do I say waiting to happen? Because recall, a force is an interaction between, necessarily, always, a force is an interaction between two particles, i.e., thing one exerts a force onto thing number two, always, right? That's always the way forces work. I exert a force on you. And by Newton's third law, you exert a force on me. But if there isn't you and me, if there aren't two things, then there ain't no force. But now what we're saying is, sorry. Is that a lowercase n for the unit of force? Yes, this was like, I'm so sorry. That was like 12 minutes ago. Yes, anywhere I wrote a lowercase n, I meant for newtons for the unit of force. Yes, great question. Great question. Sorry, I missed it. But yes, anywhere I wrote the n, I meant as in newtons for force. Yes. So a force is something Q1 does to Q2. What we're now saying, though, is a field. A field is an interaction between one particle and space. So I'll read my handwriting. What it says, the other page said a force is something one thing does to another thing, always. Like that is what a force is. A field is what a thing does to space. A field is not an interaction between two objects. It's an interaction between one object and space. The idea behind a field from here on in is that instead of from here on in, like we are mathematically, okay, wait, I'll add the math and then I'll say that. Oh, I see there's something in the chat. I will get it in 1 second. Maybe it's telling me to go back, which I will. Sorry, and I know my handwriting is becoming increasingly chaotic. I will go back in 1 second if that's what's, let me just not lose my train of thought. Let me just look at what's happening in the chat. Hold on. Oh, yeah, absolutely. I had a feeling. Okay. Great. Okay. Thank you. Awesome. Awesome. Oh, I forget how to. Okay. Okay. So now we have to be careful here. Actually, I'm going to be careful. Let me say this. Okay. So just to be clear, like the top, this equate, I guess this is a triple equal sign then. Yeah, what field is force per charge. Again, mathematically, it's nothing more complicated than the insight that a couple of you had, that if you just, it's not, mathematically what field is just like what the force would be acting on a 1 unit, a positive 1 unit receiver. That's all it is mathematically. How we picture it, what the point of it is its force per charge, right? Which means it's the force generated by one charge, but before it actually acts on another charge, it's the force that's sitting there. It's the amount of information, and it's the information that's sitting there at any given point in space, waiting for a second charge to come along and experience that information as a force. Like the reason I'm calling it a force waiting to happen is a force is not a force until two parties are involved, two particles are involved, right? But the way we now look at this, let's say that the source of our field is a point source, right? You're going to see starting next class, like we can create fields with things much more complicated than points. So I have to be careful about my equations. But let's say we have a point source, as in this problem, like a 50 coulomb positive point source. So again, what does that mean? It means like 50 times 16 quintillion protons like jammed together into like the head of a pin, right? Sitting there. The way we would talk about it now, mathematically, the field generated by this point source, the field would be a vector at any given location. So at every given location, like the field would be, go to any, picture any, how can I say this? So I'm going to start drawing drawings to help with this more. But the idea now is that you've got this. Actually, I will draw it right now. All right. So let's say we have let's say we have some positive point source called capital Q, like as in our problem, Wait, okay. Thank you for the person who just came. Thank you. I'm just looking. There is a little bit. Okay, I'm pausing for a second because. Oh, okay, okay. I see. I see. Hang on one second. Bear with me for a second. I'm sorry. There's just people coming in and out. I just want to make sure something. Attendance is just becoming a slight issue. Let's say we have this positive point source, as in the problem, as in like the 50 Coulomb positive point source that's sitting there. Now, again, it's like the capital Q. We're calling it the source because we're starting to get used to the idea, hopefully, that whichever you call the capital Q, we're thinking of that as the charge or the object or the thingy thing, the particle that is creating a force that's going to happen. Like, we're not thinking of it as the receiver, we're thinking of it as the creator or the generator of the force. So we call it the source, right? So let's imagine, but it's still a point. It's just a point with very large magnitude. So let's imagine that we have this positive point source, Q, sitting on top of our lab table. And again, what that means is we've taken a whole bunch of protons and we've jammed them together and put them in some tank or something on our lab table. Now, what I'm trying to say, if you want to picture this idea of a field, what I'm trying to say is that there won't be a force at all in the lab until there is some second charge that comes along to experience an interaction with this source. But our new idea is that even though there isn't a force yet until there's a second charge, even though there's just empty space around this source, what we can start talking about is this field that the source creates. We can depict it something like this. We could say, well, look, like at any given space, at any given location, like right here or 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 right here, like every one of these, picture that every one of these arrows I'm drawing, the tail of every arrow I'm drawing right now represents a particular location of interest, like a point in space that I'm examining or measuring or observing. The tail of each of these arrows is at some representative point in space where I'm interested to know what's going to happen if I ever put another proton there, right? And I'm going to keep going with this diagram. Let's say that I would draw an arrow like this. Draw an arrow like this. I'll draw an arrow like this. And I think you might be seeing the pattern. I'm going to keep, this is just a representative slice. Like I could draw a bunch more arrows, but this is just enough to give you the sense of the pattern. I'm going to draw a little bit more just so you really see what I'm doing. What I'm getting at is at the tail of each of these arrows, well, I'll even write that. The tail of each vector is a location of interest. A point in space that we're wondering something about. And the arrow, each arrow is a field vector. Now, I'm drawing this approximately, right? But look at the pattern. What it's saying is, if you pick any point in this pattern, if you pick just randomly, if I pick this point right here, right? If I were to look at that location in space, now it's just a location in space. There is no second charge there yet or anything like that. There's just space there. But what I'm saying is, if I know the magnitude of the point source, like I know that it's 50 coulombs positive, and if I know that this red dot that I just like, so red dot is P, location of interest. If I know that this point P is, say, 5 meters away from capital Q. So I know that it's 5 meters away, and I know that capital Q has a magnitude of 50 coulombs, right? Then I can take 50 coulombs, multiply it by the Coulomb constant, the 8.99 times 10 to the ninth number, right? Divide by 5 squared, right? Put all that information together and then multiply all that by R hat, right? So I would get this arrow right there, starting to get the red dot, this arrow. Then if, assuming all this was drawn to scale, assuming that I picked a scaling factor and all that, that arrow right at the red dot is an arrow that says any 1 unit of positive test charge, that if I put 1 positive coulomb of charge at that red dot, what the black arrow represents is 1 coulomb of test charge would be shoved up and to the left. It would be pushed by the blue source within a number of newtons represented by the length of that arrow, right? And if I go out a little farther, if I go to the next arrow, like non-coincidentally, the next arrow is saying, yeah, if you're out a little bit farther on this radial line, the next arrow says, if you were 1 coulomb of charge there, you'd be pushed out a lesser amount. And again, imagine that this whole thing is like drawn to scale, so that the size of the arrows literally represents like multiplication that we did on a sheet of paper. Then each one of these arrows, the size of the arrow represents how hard a test proton would be pushed. And the orientation of the arrow represents what direction a test proton would be pushed. So each of these arrows is a force that's waiting to happen. It hasn't happened yet because there ain't no second coulomb in the picture. I mean, there ain't no second charge in the picture. So what we're saying from here on in, this would be a vector field diagram. This would be a bunch of, what we're saying from now on, the minute you put a source charge in the lab or in outer space, you put a proton like anywhere, what we're now saying is it generates vectors everywhere in space. It generates a pattern of vectors. The pattern looks like this if it's just 1 dot. They spread out radially in space. And every one of those, I mean, we're not literally saying that there's like literally styrofoam arrows in space, right? But this is in our mind, that there's vectors, everywhere in space, and that, i.e., there's bundles of information everywhere in space that literally are newtons per coulomb. They are an amount of newtons and a direction of newtons that would be exerted on any coulomb that might ever find its way to that point. This is a field, not a force, because we're saying this information is there even before any test charge comes along to experience it. Once the test charge comes along to experience it, whatever its magnitude is gets multiplied by these field vectors, and we get a force vector. But let me make one more just to drive home the point. This would be the vector field diagram from a positive point source Q. Like that's what the vector field diagram would look like. If you're really following me, you'll understand why if I then go like this, if I go, what time is it? Oh, okay. And I know I'm like off the sheet now in a way, but this is like, but only in a way. I mean, I'm like expanding on the first side of the sheet, and then we'll get to the second side next. But if yeah, okay. But let's say we want to do the vector field diagram from a negative point source. Negative Q, right? So now we have like an electron or 50 electrons or whatever, your 50 times 16 quintillion electrons sitting on a lab table or sitting somewhere in outer space, right? And we want to know the field that it generates automatically the minute it comes into existence. Well, that field diagram, I just want to look at my color scheme. Yeah, okay, that field diagram would look very similar but different. It would look like this. I mean, that vector field diagram. It'd be the same pattern for the same reason, of vectors getting smaller and smaller as we get farther away, right? Because each vector is being drawn at a particular R, and R is in the denominator. So the farther away we are from the source, the weaker the force per charge will be, right? So, but the force per charge always points along the line of displacement. But now, so, and by the way, note this too, in both cases, it would be too crowded right there. No. Oh, something in the chat. Oh, okay. One second. Okay, just one clarification, like R, the R vector, up until now has been the displacement from Q1 to Q2, from source charge to test charge, right? Now we're talking about fields. Now the whole idea about fields now is there's no test charge anymore. Like in our minds, the test charge is a unit charge of 1. So it's not changing the numbers anymore, right? What we're talking about now is what one source does to space and does to any and everywhere in space, right? The idea of a field now is we're saying at any given location that you think of, at any given R, there is a certain magnitude and direction of force waiting to happen at that R. So now what R really means, it's not the displacement from Q1 to Q2. There is no Q2 anymore. What R is now is the displacement from Q1 to any location of interest, to any point you might call point P, any just location that we're looking at. Okay, so to summarize, so again, force is what I do to you. Field is what I do to space before you even come along. Then when you come along, the field exerts a force on you. Let me say that one more time, and then I'm going to address this diagram. I'm saying, actually, I'll say it one more time. Saying we used to say, I exert a force on you. We still say that. But now when it comes to certain kind of forces, like the gravitational force or like the electrostatic force, now what we don't say that anymore. We don't say the proton exerts an electrostatic attraction onto an electron anymore. What we say now is the proton creates an electrostatic field, and if the electron everywhere in space, it puts a bunch of vectors everywhere in space that each have a particular magnitude in a particular direction. And if an electron finds itself anywhere in space, anywhere in the neighborhood of the proton, the electron, then the electrostatic field created by the proton exerts a force onto the electron. There is now a middle agent, a middleman, a middlewoman. Like now there's a third party involved in certain kind of forces now. I don't know if this is sounding a little deja vu, maybe a little bit like source, receiver, wave, medium. Now we're talking like proton, electron, field in between. I don't know if you see that, but I'm saying now, well, that's what I'm saying. I'll say more of it. But in terms of this diagram is the exact same as the diagram on the previous page, right? It's just that the arrows are all pointing in now. Why are the arrows pointing in? Because the field is the force per unit positive charge. Anything can create a field. Anything can create a field. A positive source can create a field, or a negative source can create a field. Sorry, a positive source can create a field, or a negative source can create a field. But what the field is by definition, if you're following me, The field is the force that will be exerted by whomever onto a positive 1 unit charge. We're assuming by hypothesis, by agreement, just by convention, by the Chris trick and the direct chat person trick, we're assuming, like our calculation for the field assumes, posits that the thing that's going to receive the force, or we're imagining what the force would be exerted on a positive 1 Coulomb test charge. Therefore, if the source is positive and the test is positive, then the source is going to push out the test, right? It's going to be repulsive. In other words, from here on in, we say that positive sources create fields that push outward. They just do. They push. Positive sources create fields that go out because we're assuming, because a field is what would happen to necessarily a positive test. Similarly, a negative can create a field, like anything can create a field. But what a negative creates is field vectors that pull in, because we're again still assuming that the receiver is positive. So positives push out, imagined, hypothesized, positive receivers, and negatives pull in positive receivers. So from here on in, positive sources push, negative sources pull when we're talking about fields. Okay, again, it's another one of those things that's like simple, but like I just have to admit, like I didn't get that until I got a lot of things wrong for a long. I could never understand these diagrams. I didn't understand until I did that we could assume that the source is whatever it is, but the test is for a field is always positive. I don't know how else to say it. But all right, we'll keep going. Let me pause for a second. So this is how fields work. Okay. Last thing, and then okay, this is just to summarize. I'll just read it out loud. I said it a minute ago, but and this is just an example. Like whatever I just wrote here on the board that I'm going to read out loud, it could be a proton and a proton. It could be 2 electrons, whatever, just an example. But we no longer say a proton exerts a force on an electron, for example. We now say a proton creates a field. The field exerts a force on the electron. Right? And where does the proton create a field? And everywhere in space. It's a bunch of vector arrows in space. Now, again, let me also be clear. I mean, this is a heavy concept, right? It's simple, but it's definitely abstract, right? When I say from here on in that certain types of objects create fields, and I am saying that, I'm definitely saying that, I'm asking you to picture these fields as vectors everywhere in a pattern in space. There's going to be another way we're going to picture them starting tomorrow. But for starters, when I say a proton, the minute a proton exists, it creates a field everywhere in space. I mean, it creates a pattern of arrows radiating out from it everywhere in space, arrows that are getting shorter and shorter as they get farther and farther away, etc. Now, you might say, am I really saying that? Like, am I really supposed to believe that like for every proton in the world, there's like an infinite array of arrows everywhere in the world? Like, how literally am I supposed to take you, Yabberbaum? Like, are you really saying that these arrows everywhere in the world? Well, yes and no. Am I literally saying there are literal arrows, like actual physical, like objects that look like arrows everywhere in the world? No, I mean, I'm not saying it's Sesame Street. I don't know what that has to do with it. I'm not asking you to picture massive particular arrows all everywhere in space that would come even from just one proton, because then according to me, every proton would generate this. So, I mean, there'd be arrows. I'm not saying they're physical arrows, but here's what I am saying. The arrow is the representation in our mind for information that definitely must be in space every time any object is put in space. Let me write that down. I'm saying here's what I am saying. I'll read it out loud, my handwriting. Every point of mass and every point of charge generates a pattern of vectors spreading out through all of space. Okay, and this pattern of vectors is ultimately known as a field. And I'm saying this really happens. The minute you put you put one proton into the universe, there are arrows everywhere in the universe, like radiating out from that proton, that are getting smaller and smaller as they go. And each arrow, if you adopt a certain scaling factor, is literally indicating how big that proton is, or whether it's 2 protons or 3 protons or 4 or whatever. And it's indicating by where it's oriented, it's indicating where that proton is. Okay, I am saying that. And every bit of mass is making a bunch of arrows that point in toward it, that are getting smaller and smaller as they get farther away. And each arrow, the size of each arrow indicates how big that bit of mass is, whether it's 1 kilogram or 2 kilograms or 3. And the orientation of each arrow indicates where that bit of mass is. Now, I am literally saying this, but let's be very careful. When I say this is literally happening, arrows are just the easiest, simplest thing for me to picture in my mind, or for many physicists to picture in their mind, as to what's happening. I'm not literally saying that in the sky, there's like a line with a V at the end of it. Like, no, but I'm saying that in my mind, there's a bunch of arrows, or on a piece of paper, there's a bunch of arrows that represent something that really, really is happening, something that is real and that matters, but that isn't matter. a field is an unthingy thing. And what is it really that's really happening? I'm saying the minute that the proton is put in space, or a bit of mass, or the sun is put in space, or the earth, or a hydrogen atom, whatever, the minute an object that has mass and or charge finds itself at any location at space, what apparently must be really true to the best of our human understanding is that identifying information that describes how big this mass is or how big the charge is and where the mass is or where the charge is, a bundle of information goes to every point in the universe. And the easiest way that a bundle of information that's saying over there, there's a sun that's this many kilograms and it's over there, right? So there's like an arrow, like it's not literally an arrow, but somehow if the sun is over there, I'm saying then over here in space where the sun isn't, somehow there's information that is telling this point in space, yo, be aware. There's a gravitational source over there that's large and it's this many meters away, right? Now, the truth of the matter is, like, if there's also a Jupiter, then Jupiter's also creating a lot of arrows. I mean, I'm not denying that at all. Like, that's where this all gets very fascinating, but very quickly. But like, if the sun is over there and Jupiter's over there, then any point in space, I'm totally going to read that in 1 second. Okay, there's a great question, chat. I'm going to do it in 1 second. Let me just finish this sentence. If like there's a sun over there and there's Jupiter over there, then I'm saying at any random point in space you pick, if the only two objects in the world were the sun and Jupiter, then each one of them creates a whole array of arrows pointing toward them. And like the sun's arrows would all be bigger than all of the Jupiter arrows because the sun is more massive than Jupiter. And the sun's arrows would all be pointing in towards the sun. And the Jupiter arrows would all be pointing into Jupiter. And anywhere you stand, and this is where it gets to the back of the sheet, the second part of the homework, anywhere you stand in the universe, let's assume those are the only two things, the sun and Jupiter, then wherever you stand, there's an arrow already there from the sun. And there's also an arrow, maybe a smaller arrow, pointing in a slightly different direction, pointing towards Jupiter. And where you're standing, you experience the vector sum of those two arrows, okay? And that's literally what the homework is going to ask you to do. I'm not saying it's easy, but I'm just explaining what it is. Like because there's two sources, they would each generate their own vector in space. You would be standing in space, experience the vector sum of those two vectors. Like you'd have to add them by components, the way we used to have to add displacement vectors or velocity vectors in physics 1, whatever. And you would ultimately, and I'm totally going to read the chat in a second. And you would experience an ultimate force that is the vector sum of those two field vectors multiplied by whatever your mass or whatever your charge is. And then you'd be pulled or pushed in that direction. And I'm going to get the chat, but now I'm saying this must be the case. I'm saying, I'm picturing them as arrows because it turns out that's actually the simplest thing for me to picture, some bundle of information that is indicating both size and direction. I picture them as arrows, and physicists do. And there's another way we picture them I'm going to tell you tomorrow, but we picture them in a way that we can deal with. It's just a picture, just like graphs are not real. They're just a representation of what's happening, right? But something is happening. The thing I'm asserting, and then I will shut up for a second and look at the chat. The thing I'm asserting is that the minute there's a mass in the universe at all, any mass, the information describing the size of this mass and the location of this mass is everywhere in the universe. And that whole pattern of whatever you want to picture, whether they're vectors or curvy lines or some color splotchy like image that you could come up with on a computer, however you picture it, the information describing the size and the location of any and every given point of mass or charge, the information, the raw numbers, quantities that are describing the objects, the information is everywhere in the universe once the objects are put in the universe. This set of information, this array, this sphere of influencing, identifying information is what we call the field. The field is not material. It is not matter. It is not particular. It's not a thingy thing you can't hold in your hand, but it's totally real. as real as anything is in physics, maybe more real than a lot of things are in physics. I'm going to tell you in a second why. It started as just a mathematical device today. It started as just like a cool math shortcut to make it easier for us to, but I'm now telling you it's more than a mathematical shortcut. It's the way we actually think about the universe. And I haven't told you why that is yet. I will, or I'll try to. But whether you believe me or not, whether you like it or not, I'm saying from here on in, and then I'll pause, I'll look in the chat. From here on in, when it comes to certain kind of things like charges and masses, instead of saying that masses pull on one another or that charges push or pull on one another, what we say from now on is each mass generates a field, which is all the information describing it and where it is, the field everywhere in space. And then when a second mass comes along to any point in space, then the field at that point in space, the arrow sitting at that point in space, exerts a force on the second object, and the second object then accelerates or whatever it does. So a field is like a medium. It's like a third agent in between two objects of certain kind, of either mass or of charge. I exert a force on you, is the way we used to say it. The way we say it now is I exert a field on space. If you occupy space, you experience a force from the field at that location in space. That's the idea. It's a heavy idea. It's a simple idea, but it sure is a confusing, abstract, new idea. And it's the rest of this course is about it. Okay, but it's our next unthingy thing is fields. I'm going to pause because there's something cool in the chat, or something in the chat that I think is cool. Hold on. Wait, okay. Oh, wait. Oh, no, this is great. Wait. Oh, okay. There's two good questions in the chat. I mean, to be honest, they're from the same person, but they're sort of two different questions and they're both good. Okay, I'm looking at the time. Okay. I'm going to read the questions out of order, if that's okay. They're both good, but they may be easier for me to answer out of order. Okay, so the second question, well, I'll just read the question. Okay, here's the question, if I may. I'm not going to say the person's name, obviously, but if they go to every point in the universe, so by they, this person means like the field arrows, the field vectors, the field information. If they go to every point in the universe, which I am saying they do, yes, then how are the fields waiting to interact? Wouldn't they already be interacting? Or am I just misunderstanding? First of all, I appreciate your politeness and all that. No, but it's okay. So I'll say it again. She or he is saying, if they go to every point in the universe, then how are the fields waiting to interact? Wouldn't they already be interacting? That's a very good question. I may be misunderstanding the question, but let me say this. The person's actually really onto something in a way, because I'm just introducing this concept now. I'm being a little bit casual in my language. What you might notice that every time I wrote down the definition of field thus far, I wrote that field, like electrostatic field, is defined to be net electrostatic force per charge. Similarly, by the way, just to return, the gravitational field is net gravitational force per unit mass. Okay, now so I'm writing net. So this person in direct chat is quite right, actually, to sort of catch me in being a little bit careless with language. What I'm saying is, he or she is right. The field is the thing, is the field at a given location is the vector, arrow, or whatever bundle of information at a given location after we've already taken into account all the contributions from all of the sources around that are all creating fields. So really, so in the example that we were doing today that started all of this discussion, in the example today, we had one point source, a 50 Coulomb source sitting in the middle of the lab or sitting in the middle of the universe. And it was like, and we were testing out its effects on various possible second charges, test charges that were 5 meters away, right? And eventually we came to the conclusion, okay, let's just look at what this 150 Coulomb source is doing to any 1 Coulomb of test that could be found at a given location in space. So in the whole example that started this whole discussion, we had one point source generating our field. Now, the reality, and that's hard enough to picture in a way. I mean, that's our first introduction to field. The field is the force waiting to happen that's generated by any given source. But it's true that now what I'm saying, and what the second half of the homework gets you into is, okay, but realistically, any and every source of mass and any source of charge creates its own whole set of vectors. So it's absolutely true that a proton over here, someone's here, sorry. It's absolutely true that, wait, I'm losing, wait, I know someone's here in the, hold on, sorry, okay. It's absolutely true that a source over here of 50 coulombs will create of positive 50 coulombs, will create a bunch of arrows going out like the picture I drew, right? But then if you have another source over here of say negative 10 coulombs, then it'll generate a bunch of arrows that all have the same pattern. They're all radial, but they'll all be pointing in and they're all smaller, like 5 times smaller than the arrows from this guy, right? So technically what I should be saying, to be clear, and because it's a really good question, is this generates a bunch of arrows that we all ultimately call field contributions. Each one of these arrows generated by this source, if assuming there's any more than one source in the world, then all these arrows are called field contributions. And then all this second source over here creates a whole bunch of arrows that are all called field contributions. And then if you stand anywhere in space and you get ready to experience the field at any point in space, the field at any point in space is the vector sum, is the net effect, is at the end of the day of this contributing arrow added vectorially with this contributing arrow. So again, the person in direct that's very right to ask. What I'm really saying is that the field is the arrow that you get at the end of the day at any given location from all and any of the sources that you're taking into account that are contributing to it. Each source will contribute a bunch of arrows that we really technically call field contributions. Then all those contributions get added together to get one final field at the end of the day. And of course, in the actual universe, so now I'm going to address his or his second question in a second. Of course, if I literally want to know right now, if I literally want to know the actual absolute electrostatic field, like right here at this point in the universe, right here. Oh, if I want to be super infinitely accurate, super precise, yeah, I would have to take into account like every single proton that is everywhere in the world, like every proton in my room right here, every proton in New Jersey, every proton in the Andromeda galaxy, like, and it would be, if I really want to calculate the actual full field to all the significant digits, I would need a computer program that would be like a science fiction novel and would go on forever. I couldn't do it. I certainly couldn't do it. But we focus our attention on one set of things at a time. Like this gets to this. So like with that, we never have to take everything into account. We take the big contributors into account so this gets to the second part of the person's question. Let me get back to it. Hold on. The second part of the person's question. Oh, and then wait, okay, then there's another question, I'll get to that. But see, the second thing that this person asked in direct chat, these are great questions. She or he said, because at some point, I imagine the force gets so small, it's no longer, it's no longer measurable, or in other words, it's negligible, the person said. So would that be like the cutoff for like the field range? Right, exactly. Like notice this. The R, yes, the R squared in the denominator tells us two things. It tells us a lot of things, but a couple important things. On the one hand, no matter how big, like you can make R as big as you like. And as long as R is a number, even if it's 4.5 billion light years in distance, right? If R is any number, no matter how big, then the fraction that you generate in the equation, the force that you get, or the field result that you get, is going to be some number. Like as long as the denominator is finite, no matter how big it is, then the force will be finite, no matter how small it is. So on the one end, I'm saying, yes, like any proton over here creates arrows forever that are getting smaller and smaller and smaller. But even as I get to the edge of the universe, there's a tiny, still finitely large, but tiny arrow way at the edge of the galaxy that's coming from this proton right here. So on the one hand, yeah, like these things go on forever, and there's no actual end to the effect on the universe of any one given particle in the universe. But the flip side is what the person's also saying in direct chat, which is, but hang on, once R gets big enough, F is going to get small enough that even though it's still finite, even though it's still not zero, it's going to drop below the threshold of whatever device I'm using to make a measurement. And this is where science becomes incredibly practical. This is where science is like so real. This whole idea of like the distinction between science and math is about all numbers and all relations throughout the universe. I love it. It's math is the language in which the universe thinks, but science is that language applied to numbers that we obtain only through measurement. So once we reach the threshold of a measuring device, once something is no longer detected by whatever whether it's a micrometer in the lab or a Hubble telescope in outer space, once something, even though we know it's there, if we can't distinguish its size from the size of anything else on our measuring equipment, then it's dropped below the threshold, and then we call it like in the limit as the approaches zero, right? Literally, I mean, for me, this is where I didn't understand calculus at all until I started thinking of it in a science context. Limits are in calculus, which sounds so weird in a math, well, to me, they seem so non-mathematical in a math class. But what a limit is something that's dropped below or above the threshold of measurement. So we're not saying it's not there. We know it is there. And we're not saying it doesn't matter, but we're saying right now, we can't quantify it. So it doesn't go into our calculations. It is non-quantifiable. Maybe some, right? So, but that gives us a huge amount of freedom, because then that means I can make problems. We can think about, okay, what's the field in the lab that is generated by, or what's the field over here in this location in our isolated protected lab? What's the field in this location over here due to the hydrogen atom that's over there and the lithium atom that's over there, right? We can realistically say, let's find the field at this location due to the addition of the two vectors, one from the hydrogen atom that we placed over here, one from the lithium atom that we placed over there. And we could say, we did a really good job in this lab of isolating from all other effects. Like we've gotten rid of as much as we can. And yes, we're not perfect. We know that. There still are effects and things in the lab, and there's still electrons in the Andromeda galaxy that are actually affecting this thing, but not large enough to be detected by our measuring equipment. So our measuring equipment is only concerned with the field from these two vectors. I'm totally going back to the chat in a second. I know there's at least one more thing in the chat, but all of this is to say, first of all, it's a great question. It totally shows you're paying attention. But second, there's two questions. But second of all, as far as if I keep yammering like this, the homework that's left, I mean, the problems that are left on that homework sheet, what they're literally asking to do now is to just go, like, it's hard enough. We've spent all this time discussing the very abstract new idea of what it means for 1 point mass or 1 point charge to create a field at locations in space. That's already a new enough concept. That's a big concept. And by the way, it's a real thing. It's a concept, but it's a real concept. That's big enough, right? Just the field coming from 1 point source. What this person's asking in chat and what the homework then asks you to do is now take a kind of an enormous leap and say, let's now imagine there's 2 points. In fact, I know there's still more in the chat, but I'm going to literally switch screens in a second. I'm going to switch screens. I'm going to try to help you with this homework before I lose sight completely. I will go back to the chat in a second. I promise. Hold on. Where are we? I'm going to switch screens. How do I do it? 1 second. Okay, and I know there's someone in the chat. I will get him or her in a moment. Okay, just so you know where this is all heading. And again, I love it. The reason I'm excited is Nothing pleases me more than when there's a question in the chat where the person thinks that they're not getting something, but actually they're just asking the next reasonable question that generates the next homework question. Like, it just goes to show all of this is what you guys would, what you people would think of on your own if you had nothing else to think about. If you had no other stresses in your life and this was your only priority, your mind would progress in the same direction as the ancient and classical physicist minds progress. Their minds just got there faster because it's all they were thinking about. I mean, are you on it, right? But it's not black magic. It actually is a logical progression of thought. And so the next thing that happens, before I go back to the chat, is like, I think you see, yeah, you see, on the next homework, we now have 2-point charges of differing magnitudes held stationary in an enormously spacious XY plane, right? Okay, so it gives you the data. It first is going to ask you to create a diagram. So you're going to put like a positive 5 Coulomb charge up at like the coordinates 5,4, right? And then the coordinates are sort of unfortunate, like you have to sort of make a big graph, whatever. But then you're going to put a -2 at coordinates 10,3. So they're all in the first quadrant. I don't really know why. So you got these 2 charges, okay, 2 sources. This is totally the question that was being asked in the chat, I think. And then your location of interest, what textbooks or websites might call the field point. The point of space where you're interested in getting the field is the origin, 0, 0, right? And then it gives you the Coulomb constant, right? And it says you can round it to 9 times 10 to the 9, 9 times 10 to the 9th. And I'm telling you now, just like I did today, if you want to round that even further to 1 times 10 to the 10th, knock yourself out, do that. It'll make this a lot easier to picture and to do. You won't get bogged down in as much computation. Okay, so you're supposed to draw a sketch. I promise. It seems like I'm totally forgetting the chat. I kind of am, but I'm not permanently. But I think this will make this more concrete for everybody. It asks you to draw a clear sketch of the situation. So you're going to draw like a Q1 and a Q2 at the appropriate points in that XY plane, in that first quadrant, right? And then, and like Hema taught you, like, you got to show that, like, okay, pick a direction, like say that when the x-axis is going to the right, you're going to call that positive or something. And when the y-axis is going up, you're going to call that positive. I would recommend something like that. Then I'm going to tell you right now where it says draw a neat and clear sketch. Then I recommend, before you do anything further, draw an arrow coming out. Sorry, you're going to draw. Now, actually, listen to me carefully. I can't write this down, but this is to help you with this homework. It is part of your sketch. You're going to draw 2 arrows, 2 vectors, each of which should be emanating from the origin. Like, you're going to draw 2 arrows. For both of those arrows, the tail, for each of those arrows, the tail will be at the origin, because the origin is the, like, 0, 0 is the place that we want ultimately to compute the field. Like, the purpose of this question is we want to find out what would happen to a positive 1 Coulomb of test charge if it were located at 0, 0. What would happen to it? How hard would it be pushed or pulled, and in what direction, as the net result of both of those sources that are somewhere in the first quadrant? Like, one of them is positive, one's negative, right? Like, our ultimate goal is to find out what the field, the net effect, the sum of these 2 field contributions would be on a test charge if it were located at the origin. Now, again, there is no charge at the location. That's why we're calculating field, not force. We're calculating what force is waiting to happen, what net force is waiting to happen at the origin. I'm going to go a little further because I'm making the bet that this is helpful to Maria, and I promise I will get the thing in the chat. I just don't want to break my train of thought. And I know that by the time I got to the thing in the chat, it's going to be completely moot and everybody's going to be frustrated. Sorry. But I'm telling you right now that there's going to be 2 arrows at that origin. One of them is going to be like one of them is going to be pointing away directly from your positive charge, right? Positives push. One of those arrows would be like the continuation of a dotted line that could be drawn from the origin to your positive charge. And the other arrow will be like a continuation of a dotted line that you could imagine or draw from the origin to your negative charge. But that arrow, the one that's from the negative charge, will be pointing to the negative charge, if you follow what I'm saying. So you'll have an arrow coming out of the origin, parallel to the displacement from the positive, and you'll have an arrow coming into the sorry, I'm saying that wrong. I mean, both arrows have to come out of the origin. They're both having tails at the origin, but one of them will be a pull and one will be a push. I'm saying one of them will be going away from the line, the dotted line that connects to the positive source, and one will be pointing along the dotted line that connects you to the negative source. I might even draw this in a second if I have time. But the last thing I'm going to say for the moment is you're going to have two in your sketch. You should have two arrows at the origin. Each of those arrows represents what I was calling before the field contribution from each one of those sources. Your job in the math is to, now that you have that picture of the situation, now somewhere else on your piece of paper, you're going to transpose those two arrows. You're going to move them, translate them on the page. Somewhere else on the piece of paper, you're going to preserve the length and the orientation of each one of those arrows, but you're now going to put them tip to tail somewhere else on the piece of paper, because your job is to add them, because you want to get the total field effect at that. And it's not easy. I mean, if I get a chance, I'll say more about it in a minute, but your job is to do the vector sum of those two vectors. Each one of those vectors is given by the equation that we have, the KQ over R squared, R hat thing. But you're going to add those two vectors together. And let me warn you right now, and if I have 3 minutes after I look at the chat, I'll try to break it down further for you. But let me warn you right now, when you add those two vectors, since they are not parallel nor perpendicular, the only way you can add them is to separately get the X and Y component of each one. Like, that is the strategy for this problem. If you do it, it's not hard, but it is a little bit thick. You're going to take each arrow and do what you used to do in physics 1, wherever you went to school. Like, you take an arrow and you draw its components, its X component, its Y component, like keep tips and tails on everything. Don't lose sight of direction. And you separately get the X and Y component for each arrow, and you separately add the X components together to get one big X component. You separately add the Y components together to get one big Y component, and you put the X component and you create one final last Pythagorean triangle with one big X component and one big Y component. And the answer that you're looking for at the end of the day is the hypotenuse to that one big triangle. And it will have a direction. What will the direction? So that will be the magnitude, the length of the hypotenuse. What will the direction be? Whatever angle is formed between that hypotenuse and the horizontal base of the triangle. Right, and I just said a lot, and I didn't write it down. I may, in 1 minute, try to sort of write it down, but that's how you do the problem. If you get even roughly what I'm saying, if you hear what I'm saying and you're like, "Ugh, I don't want to do that," well, that probably means you do understand what I'm saying. So that's good, because it is a little bit much. But that's just understand what you're trying to get the field from 2 points. We're only going to do this once. It will be on the final exam. We're only going to do it once. You're going to do it once just to see how annoying it is, even to get the field from 2 points. Can you imagine getting the field from 3 or 4, or let alone the whole universe? It gets very heavy very fast, which is why the rest of this course is techniques that have been developed for how to deal with anything more than 2 points, because it's so much computation. So you're never going to have to do anything worse than that. But you have to do that once to see what's going on. Okay, I'm going to pause for a second. I know we have 6 minutes. I'm going to look at, although actually, I'm going to stop this. Can you just put up your electronic, if you sort of got, I know that was a lot, but if you sort of think that you get the basic procedure of what I'm asking you to do okay, that's one. Thank you, Dante. That's okay, cool. Cool. Thank you. And that doesn't mean you're great. Awesome. That makes me very happy. Okay. So now I'm going to, that's awesome. So I'm going to get this chat person. There may be more than one chat. Let me see. Hold on. Oh, yeah. Well, okay. I'm going backwards. I'm looking at the matrix joke. Yeah. I mean, don't get me started on the matrix, but yeah. Okay, I'm just gonna say this about that joke. If we do know that we're not in the matrix, sure, this is how, but are you sure we're not in the matrix? Okay, wait, now let me look at this direct chat. Oh yeah, wait, no. So wait, someone asked in the direct chat, just to be clear. Yeah, anytime I've ever on that sheet, on the yesterday sheet and all the notes, I very deliberately made the gravity equation negative. The gravity equation is supposed to be negative. There is a typo on this homework sheet. Please correct it right now. I mentioned this at the beginning of class, but no, there's a typo on this homework sheet that we're talking about right now. When it gives the gravity equation there, it literally just accidentally left off the negative sign. Whenever gravity equation is expressed as a proper force vector, whenever it's expressed properly as a vector equation, whenever we're actually tracking direction carefully and rigorously, gravity should always be a negative because gravity is attractive. Yes, I just accidentally left it off. Oh, okay, cool. Great question, direct chat person. Awesome. And thank you for acknowledging. Okay, so that's that. Now, we have Mrs. Google's like, how can I help? Well, do you know a good psychiatrist? I don't know. Okay, let me go. We have 4 minutes. Let me pause for a second. Okay, I'm tempted to say this. This has been a lot. I could stop right now and draw the thing that I was just saying to everybody, but I feel like that's probably overkill. If you feel like you understand the thing I was just saying, since we never took a break at all, and this was a lot, and the homework that's due tomorrow, and I still owe you your exams, I'm happy to say, if you're done, I'm done. We can be done. It's only 4 minutes, but I don't usually, I'm good if you guys are good to say goodbye. And I do have to wait to talk to a couple to answer questions. I'll be still here, and there's at least 2 of you that I want to talk to or whatever, but like, if you're good, I'm good. Have a nice evening. Assume you're good. Oh, thank you. Okay, thank you, Juliana. Okay, thank you. So goodbye, and I'll turn off the. I'm here. I'm not going here, but goodbye. Have a good night. Thank you, guys. Thank you. All right, let me turn. Thank you. And I'm still hanging out. Oh, yes. All right. And so hold on, let me say this. So a couple of you I know are hanging out because either I asked you to or you asked if you could, which is good. So bear with me for a second. If either I asked you to hang out for a second or you're waiting, I appreciate it. Please do wait. But he just said goodbye. All right. So he wasn't. Okay. So wait. Oh, have a nice day. Okay. So goodbye. Have a nice day. Thank you. Okay. Hang on. Okay. And we'll stop the recording. Oh, wait. Hang on a second. Panita, wait. Hang on a second, please. Wait, one second. Okay, yes. Wait. And let me just